Okay, so good evening, everyone. We are discussing mobile app performance today, and we are discussing it from points of view, three different points of view. Let's start with development and go until the external factors that also influence mobile app performance, such as network protocols, for example. That's why we have these three amazing speakers tonight. Thank you so much for joining and for accepting being here today. And thank you as well for coming. We are Codavel, a Portuguese tech startup. We are based in Porto and here in San Francisco. And we actually want to discuss mobile app performance because we really believe that it should be a topic that we should be discussing today because it's super important. We don't actually discuss it very often as we should. Usually people only look for the app or at the app, and that's not only it. So Rui, which is our CEO, is going to introduce the speakers today, and he will be moderating the panel. So good night and enjoy, everyone.
Hi everyone, as Lily mentioned, I'm Rui, CEO at Codavel. So like in a nutshell, what we do is we have an SDK that basically speed ups mobile apps. But I guess today, like the goal is to have hear the experience from our fantastic speakers today. We have Rudro from Uber, more from a development and monitoring perspective, if I'm not mistaken. Then we have Swapnil that is going to take a look at app performance more from a consumer perspective. And then Subov from a networking perspective. So I guess that the whole purpose of this is to take a look at app performance for a holistic perspective. And so without further ado, I would like to invite Rudo to start.
All right. Yeah, let me start presenting. Okay, so I'll try to see how much I can fit into the 20 minutes. I'll do some slides and I'll also go through some actual sessions with instruments just to show you about some of the things I'm talking about. So I'm going to focus on two main things today, which is basically I'll talk about visualization and why I think it's actually really important. The out-of-the-box tool for looking at performance on. So sorry, this is a little bit iOS specific. Though hopefully the learnings I'll be talking about are general and apply anywhere, but specifically my experiences with the iOS side of things. So I'll talk about like looking at stack sampling data with instruments and why I think it's really important to visualize that data and why that's useful. And then I'll talk about like sort of these gaps that we found when we worked. So specifically, as with every large company, we have a period where we rewrote our app from scratch in Swift, and everything was great. And then, of course, a year and a half later, people started noticing the usual thing, like, hey, it used to be awesome. Everything would launch really fast. What happened? Where did we go wrong? And so I'm on a mobile platform team, and so we were brought in to like look at all of these bottlenecks. So I won't talk about what we did. I'm just going to talk about the learnings from that, like what tools I found were critical in getting that work done, in getting our like startup times down, and in getting our tap times down. There are a lot of complex interactions in the Uber app. Anyway, so I'm going to kind of assume that people basically know what stack sampling is. So hopefully everyone knows that the most common way to find a bottleneck of performance in your app is you run instruments, you take the time tracing tool, and by default out of the box, it samples your app every 1 millisecond. For those who don't know, it's absolutely critical that if you find there's a setting where there's a checkbox for high frequency, and you really, really want to check that checkbox because it goes from 1 millisecond down to 100 microseconds. So I feel like otherwise it's super coarse. Anyway, so you really have two options of looking at performance. So you can either do time spans where you're doing sort of start-stop measurements. So for coarse-grained stuff, like really critical interactions in your app, you want to put an actual manual start time, stop time sort of thing. But for the most part, if you don't want to go and do this manual work, what you can do is just use stack sampling. So as we talked about, you just launch instruments, you pick the time sampler, and you can go. You don't have to touch your code. It's very fast. It's very quick to get started. And it's good for finding sort of aggregate data and finding hotspots in your application. The problem is that this data, so you don't need to read anything on the right side, but that's the normal the interface of instruments when you do a time profile. And so finding the hotspots is really hard because what it does is that once you time sample your application over a certain period, what instruments is doing is it's collecting all of the stacks, putting them together, and then aggregating the most expensive, the most common stacks that show up. So you can find the sort of the most hit path in your application very quickly because instrument surfaces that. What this screenshot was trying to show is that I'm highlighting that there's actually like 4 different performance problems in this app, but you can only see the top one. So let's actually see if we can kind of do this in real time. So this is an open source tool that we have, and this is a sample running on it. So the main thing is that when you pick, so that thing that's highlighted is a main thread, and so when you pick this, when you pick the main thread and you focus in on it, then on the right side, what happens is you can see that there is a most expensive stack. In this particular case, it's like figuring out file URLs for the files it's supposed to scan. And that accounts for 85% of the time. But what's really hard to do, and this is just like kind of a throwaway example, but so in this case, 85% is pretty high. So maybe this is all I need to fix, is that that particular code path where it ends up there is the most important thing to fix because 85% of your time is going there. But what would be nice to know is that it would be nice to know if that's the only bottleneck in my app or are there others. So one of the tools I wrote, there's a very quick and dirty tool, which there's this trick in instruments where you can do a deep copy. So when you do this, what it does is all of that data you're seeing in that table on the bottom got copied onto the pasteboard. So you could paste it, but you can also take that data, and I wrote a little Python script that reads that data and then visualizes it like this is a flame graph. So now, instead of knowing just the hotspot, the single hotspot, I can instantly see, so this graph is visualizing exactly the same data that's in this very dense table that's super hard to read, right? So the hard part is finding what's the second most common stack here. And you have to like drive down, sort of get RSI, trying to like click right arrow down until you like find all these hotspots. This visualization of that is the exact same information just done as a flame graph. So this way I can find that there is like this file manager that's kind of a bottleneck. So you can see as I hover over, you get times and stuff. And then there's some sort of like URL directory creation that's a bottleneck. And then you can find there's a bottleneck here and a bottleneck here. And of course, you could zoom into like one specific thing. And then once you zoom in, you can like find what the problems are in that thing. So there's nothing new. There's no new data that I'm showing here. All I'm trying to demonstrate is that it's really important that when you encounter, when you encounter this sort of data dense view in instruments, I've found it very helpful to visualize at the top level perspective. Specifically, I was working on app launch performance, and that is at least unfortunately for the Uber Rider app, that is a multi-second process. So looking at that much data in a table like this is crazy. So looking at it, visualize as a flame graph was super useful for me. And so there are a bunch of tools. Again, you can come talk to me afterwards if this sort of stuff is interesting to you. But there are a bunch of tools to like turn that data so that it's a much more manageable thing. So that was the flame graph that I just demoed. So there's one other problem that I think people rarely ever talk about when they look at time sampling. So if you sample your app using a time sampler and you collect all that data together, then you can do what I just went through, which is you find the hotspots, you find functions that are bottlenecks, the stuff that gets called thousands or millions of times, or are just expensive because they're doing intensive graphics or computation. But there's another aspect of all of this that people, I feel like, don't talk about enough, which is that there is a subtle difference that most people don't understand between flame graphs and flame charts. So a lot of people have seen, maybe you've seen this inside of Chrome, there's a utility that lets you visualize time traces. So if you go to your browser and just type chrome://tracing, there's a little built-in tool that's just built in by default. It's not a plugin or anything. It's just there in all copies of Chrome. And you can look at these time traces over, and this, as you can see, looks very similar to the flame graphs that I was talking about. The only difference is that when you look at a flame graph, that's just the width of each of these bars in a flame graph is just how many times that thing happened. The difference here is that, and so the x-axis, as you go from left to right, that is not time passing by. It is just the count of function calls. The difference here with a flame chart is very subtle. The flame chart is that there is actually time passing by on the x-axis. And so what happens is that, I'll kind of skip ahead because I don't have that much time, right? So basically what's happening is that when sampling is even, what you're doing is you're saying that, okay, I have samples coming in every 1 millisecond. So overall, the structure of my flame graph looks like the thing on the right side. But sometimes what ends up happening is their sampling is uneven. So there are samples coming in and there are these big gaps in the middle. So when people build tools to take the sample data and turn it into a flame chart, what they're doing is that they've just, we don't know what is happening in that big area, that red area in the middle. We have no idea what's happening because we just sampled the app and all we know is that we don't have a sample in the middle. So of course, there's only one option here, which is you just smear time, right? You're just smearing that stack on the left and just assuming that that's the same thing that happened all the way through. So this way, so what basically ended up happening is that if you go into instruments, let's see if we can demo this. Yeah. So if I go to the main thread, and you can't read any of this, but you'll just have to trust me. So if I highlight a 200 millisecond, so there you can see this filter on the top. So I'm highlighting a 200 millisecond section over here, and I want to know what's going on in these 200 milliseconds, right? But the funny thing is, if you look at that number that you can't read on the highlighted side, the leftmost number says 127 milliseconds. And the reason why that is, there's this discrepancy, and this discrepancy is what bothered me a lot because I'm trying to optimize like a 5-second startup time. So this discrepancy mattered a lot to me, which is like, where does the rest of the time go? And the rest of the time is, and there's another random pro tip for instruments, is if you zoom in far enough, you can see individual stack samples one at a time. So you can see exactly the problem here, which is that when things are good, that's on the left side over there, you have these even dots spaced 1 millisecond apart. But when things aren't working out, there's these gaps in the middle. And so basically what's happening is that there is a variety of explanations of why there are gaps in time. So some super obvious explanations are, well, it's just because your app was not running. Another explanation would be that your thread is not running because some other thread, you have a heavily multi-threaded app, the other thread is running and this one is not. But what basically I found is that you can figure out, and again, I'll kind of skip over this, but there's a separate instrument called the system trace instrument, and this allows you to see every single system call that's happening and how long the latency of those things are. And basically what I found is that it's really critical to try and drill into all of these spaces. Because if you're looking at a multi-second interaction, which would only be for startup, but even for our taps, there are interactions that take maybe like half a second or so, which is really too long. And we want to get those down to like 300 milliseconds. So when you reach these scenarios, it's really important to understand those gaps that I showed you. And what happens is that by using a thing like a system trace instrument, you can find that there are periods of time when your app is actually locked. So another good explanation would be that it's network I/O or it's disk I/O. So that's a classic explanation of why there are missing time samples. It's because you started to read something from disk, and then of course your thread went to sleep and then woke up 50 milliseconds later. So in instruments, when you look at the data in aggregate, those 50 milliseconds are never accounted for. That table does not account for the gaps in it. So this thing is that for startup, this was critical for me to look at those gaps and understand what was going on. And it surprised me because the obvious stuff is disk I/O, network I/O, these things we all understand. There are entire companies looking at how can we reduce latency of networking, how can I make disk reads faster. That's pretty obvious. The non-obvious stuff to me is that there are unexpected locks in a lot of places. So Swift has a lot of internal data structures that it locks. So one of the things you can find out by using things like system traces is that there's a lot of times where just because Swift underneath is looking at some shared data structure, it needs to lock, and it's causing these stutters in our app that like we thought, oh yeah, that's just context switching out to another thread, it's not our fault. Actually, it turned out that, well, it's indirectly our fault. We're using standard Swift, like standard library calls, and you can see here, I forget what examples I put up, but this is actually one of them is an actual request on the right, but then there are other ones which actually had like a Swift array that has a lock while it's like releasing something. So we found that there were a lot of interesting like gaps like this that we found in the standard library that we weren't considering when we looked at all the data in aggregate. So this is something I feel like people don't really talk about. So it's just a sort of a pet peeve of mine that people look at the aggregate data, and that's great for finding, like really intensive math like hotspots in your application or graphics hotspots. That's great because you do have samples and you can look at the aggregate data. But there are a lot of scenarios like this. And if you really care about like going the last mile and optimizing like all the way down to the like last millisecond, then it's important to realize that there's this whole next level of performance you need to deal with, which is that there are internal locks, there's I/O, there's a lot of other stuff that you can find. And I'll actually stop there. I don't know how long I spent. I still have time? Okay, so I can show you really quickly then what, why this system, okay, great. So I'll open up, oops, that is not what I meant to do. So if you do the same exact thing, this is again sampling that same open source app, but this time using the system trace, there's a lot of data and it's a little overwhelming, but you can kind of work through it. So what the system trace instrument does um, is that, yeah, so it has context switches, it has system calls made, and it has that all broken down by thread. So what you can do is if you run the system trace instrument, so basically you would say new, and there's system trace is one of these, yeah, over here on the bottom. So you'd use one of those. And if you do that, then for this given thread, what you can see is all these red things are system calls being made. And you can really zoom in and find specifically like what system call was being made. So there's a little display at the bottom, again, which you can't read, but it tells you exactly which like system calls are happening right now. So you have event system calls, and you can find every single system call and the latency of them. So exploring this data allowed us to find like exactly the precise moments where there were those gaps that I was complaining about, and to try and decipher like why is it that there's a gap in the thread. And so this is where you can kind of see that there's a lot of locking going on. And the cool thing about this instrument is that on the right side, for every single system call, there's a full stack trace of where it comes from. So it's possible to actually find exactly where. So this one, this is a very random one, for example. So this is a lock. So the highlighted row says ulock wait. But you look at the stack on the right side, the last known thing is a NS regular expression dialog. So there's a lot of this stuff that you can't do anything about. So this is a good example of that, where this is some deep down thing inside of NS regular expressions where the dialog grabs a lock before it can let go of some memory or something like that. I'm not sure what I would do about this. It's really not a lot to do with this data, but there are definitely cases where you find that these locks and stuff are your fault, or at least directly enough related to your code so that you can like get rid of them. So again, this is not something everybody should do. You should definitely stick with the time sampler instruments for the course level stuff. But if you're really obsessed about it and you've kind of run out of options when you've looked at the hotspots, then I would encourage like looking into the system trace instrument. And then this gives you a very detailed explanation. So not only does it have all the system calls, but also on top of it, these bars, which you can, again, you can read, is the one I'm highlighting over here. It says preempted. And then the blue bar over here where the mouse is, it says running. So you can actually see exactly when your threads are being preempted by other threads and running. So it, again, allows you to get to that next level of performance polish once you've found like the coarse bottlenecks. You want to drop down here, especially if you're writing like system level libraries as well. We focus on this to make sure that if we have a storage library or something like that, we use this instrument to make sure that there is a reasonable amount of I/O happening and that there aren't like random multi-threaded locks that we didn't need. So it gave us a level of detail that we didn't have before. And it's also one thing that similar to like people not talking about these gaps in time tracing, it seems like everybody always talks about stack sampling and looking at stack data, but people don't like look at sort of system calls and context switches and all this other like sort of lower level stuff. But it is actually easy to do. You can just, again, launch instruments, pick the system trace instrument, and you should be able to do this right now in your iOS app without having to touch any code or anything. This should not take any extra work on your part, so that's kind of cool. Yep, I think I'll stop there. Yeah.
So I don't know if the audience, we have time like for 2 to 3 questions. Does anyone has a question right now? Don't be shy.
Awesome thing that you are trying to do and trying to achieve. My question is, everything that you presented is really like you do it offline. So
Yes.
you sample everything, you run an experiment,
Yeah,
and then
this is
like you,
all
you then
locally.
present.
Yes, yes.
How
Um,
can we
yeah,
as developers, as
yeah,
product managers, engineers,
yeah,
try to converge all of these ideas towards more of a
yeah,
continuous
yeah.
deployment,
Yeah. So
design
the
thinking or
right. So there are two different parts of this. So one is that, of course, we want this data in the field from our real customers. Um, Obviously, stack sampling at a millisecond or 100 microsecond thing is impossible on a real device. So what we do have is we do have something called a performance SDK, which allows us to make very coarse level spans. So they're manually inserted start stops. And that data does get aggregated. It gets subsampled because a lot of information, but that data does get sent up to our servers just along with our analytics and other normal data everybody collects. So that allows us to look at our most important little spans, the most important taps in our app, and we track all of that in real time, and then we can slice by device and country and stuff like that. So there are definitely dashboards that are tracking all of this live for real customers. But it's just impossible to do at this level. So at that point, we just get the data that this screen is slow, or we find out things like the most important tap in the Uber app is when you tap the request button to get a car. Obviously, we want to make sure the next screen instantly shows up. So we track those times, but there's no way to fix that with that data. That's just to keep track of things, and you have to do everything I described to actually fix the problem. And the second thing, which we're trying out right now, is that we, of course, spend so much time, like weeks, trying to fix the performance issues. Of course, we don't want to hear 6 months later the same thing, and people come back and say, "Oh, it was great after you guys fixed it, but like, what happened? Where did we go wrong?" So we don't want to repeat the cycle once a year. So what we have now, and this is very challenging, is that there's a device lab that runs a whole suite of performance tests on real devices for every diff that lands on master. So we have a system in CI now that's tracking it. It's just very hard to deal with the noise of these things. So we'll have to find out, because if everybody introduces like a millisecond delay, then after a year we'll still be screwed. But hopefully we will catch the big jumps in performance. So there is a system right now for both Android and iOS that is running every diff through a set of performance tests, tracking the numbers, which are noisy, trying to use machine learning so we don't have a lot of false positives, because then the systems do so. But dude, we do have stuff like that. It's very challenging to get that data, to get it across a range of devices so that it's actionable. So we're struggling with that, but this has been built, it's live. I just can't say whether it's successful or not yet. I just know we built it and we're trying to make it work. But anything else?
One more question?
Yeah. We've never seen that. Yeah, we've tried to measure the overhead of it. As far as like definitely visually, it doesn't seem to make a difference. Like looking at it, just eyeballing the speed, like because if it was like a 20% drop, hopefully I would be able to see. But yeah, it does seem to be. So again, because we have the manual measurements as well, I can cross-check sort of the manual spans with the instruments thing. And the other cool thing we can do, which I didn't talk about, is for the manual spans, it would be nice to overlay the manual start-stop timing inside of instruments. So there is something called signposts in instruments that you can drop. So I did actually write the code to take all our manual spans and drop signposts. So then I can visualize the start-stop wall clock timing stuff inside of instruments as little bars in the signpost track, and then cross-check that with running the app without instruments, seeing how long the manual start-stop timing spans set according to wall clock time, and that gives me a cross-check of like, yes, there's a dilation of 3 or 5%, but enough that we've never bothered worrying about it. It's been like 2 to 3% typically. So it's not.
So thank you, Rodro. And now let's welcome Swapnil. All set? So that's why network calls have to be fast. That's one of the reasons why they have to be fast. Let me know.
Thanks, Vi. Hey guys, I'm Swapnil. Pretty excited to be here. Today I'm gonna cover the developing mobile apps for the performance keeping in your mind, right? Now, definitely I am a geek inside, but today I'm gonna take a consumer focus, right? And I'm gonna basically go through some of the lessons I learned, and I probably gonna keep with me for lifelong, right? So we'll go through like a couple of those lessons. A little bit about me and my background. I joined Yahoo as an SDK engineering manager, and then now I'm heading the same group. Fast forward 4 years, it became Oath, same desk, nothing changed, except the increase in responsibilities and the bigger team. And then now, fast forward 1.5 years more. As of last month, we became Verizon Media, right? So it's the same company, same group, just like broader horizon. Right. And the fun fact for today is who helped me creating this presentation is my 4-year-old. And we'll introduce her like later in one of the slides, like why she's more important when I prepared this presentation. But let's go through it. Right. So this is very familiar, right? As an app developer, when I am in like some of the things that my PM comes to me and say, hey, we are losing the DAUs, right? And I'm like, no, my app works perfectly. I have 100% of performance is passing on my test environment, right? And then he was like, no, but I can see that the user session time has decreased since last couple of months. And I was like, yeah, but my app was spotless, right? Try it out. I am on the company network. I am on 4G or 5G or LTE, right? And I was like, yeah, but then still, like, this thing is not adding up, right? And and then we start thinking, like, are we actually collecting data and are we actually measuring the performance of the app correct, right? So that's where, like, the whole thing starts. Now, if you look from the user's perspective, and before even going there, like, if you think about it, like Dilbert is my favorite thing, right? I mean, probably the first thing I look up whenever, especially on the weekends. So you are like almost ready to launch, and as a team you are working towards your launch. It's like, hey, are we ready for the beta users? It's like, no, maybe performance is not that important here, right? It even if it takes like a few more seconds to launch your app, probably fine, may crash, beta users understand, but then as you go towards your launch, you'll be like, hey, are we really ready, right? Are we going to actually engage customers? And when engagement, as you mean, like that they want to come back to your app every single day, right? I mean, you don't want to like one-off users who come in and go off, like they finish their work. Uh, I think that's your side of the story. But then security engineers, we call them paranoids, right? They are paranoid enough always, and they come back and say like, did you actually secure our product, right? So there is always a tension between like the product side of the things and security side of the things, but at the same time, the first and foremost, you don't need to like lose focus on the users, right? So that's my talk today, like being user first, but at the same time, like developing for app performance. All right, so what matters to the users? Like what matters to like my 4-year-old, as I was saying, or my mom or dad, right? You have different demographic and age group of the users, and what matters to them is app performance, right? And I'm gonna like take a pause, and I'm gonna introduce my daughter. Her name is Shaima. She's 4-year-old, as I said, and this kind of stuck me. So as being a 4 years, she's like very much into Peppa Pig, which is kind of a European thing, right? And then she's also interested in like Dora and stuff. And the other day, like she was like, "Hey, can you put Peppa Pig?" And I was like, "Yeah." And then I was looking my remote. I was trying to turn my TV on. It was like, I want to see Peppa Pig in YouTube. I was like, no, the show is already recorded on Amazon Video as well. And I was gonna go there, but it's like, no, my preference is to go to YouTube. And I was like, what happened? And in her broken English, she said, you know what, when we last time did that, it was just circle, circle, and circle. I was like, okay. So imagine, like, my 4-year-old can develop that brand love and brand loyalty, right, towards YouTube. And I'm not saying, like, there is anything wrong between one service or the other. Probably on that fine day, my Comcast router has decided to, like, not give enough bandwidth for that particular show, right? But user create their loyalty and their brand love pretty early in their, like, cycle when they start adopting these applications, right? And the biggest learning point is, if you can provide them app performance, they're gonna come back. If not, then they're gonna turn away. There's a lot of competitors out there. All right. So what's important when I look at the performance? There are three things, right? Basically, you're looking at latency, and then when I say latency, it's actually user perceived performance. It doesn't matter how many gazillion or million network calls you are making underneath, right? Whether your main thread is hogging or not, you're doing things off background thread, off main thread in background thread or not. What it matters to them is that perceived latency, how fast they can get into the app, right? The second thing is stability, which is mainly crash rate. So first thing is when you app the launch, and the second thing is when you start using the app while you are in the app, what matters the most, which is stability, right? It should not crash. You should have user feedback. You also should have, like, proper way of doing things in your background queues or not on the main thread, right? A lot of things. And then this third thing is battery performance. Who wants to turn their phone into, like, a hot powerhouse kind of a thing, right? I mean, user will, like, go light away. Even when the hardware and other things are increasing in the capabilities, battery is always the main concern, right? Because you want to last that battery for about 24 hours. So today itself, the thing that I'm going to focus on, the highlighted stuff, whatever I learned from, like, the app performance in the user perceived latency side. All right. So you are an user. Like, I mean, I daily habit, like, I go in the morning and go through, like, my finance. I look at my portfolio. I go through Google News. I go through Yahoo Mail. I go through my corporate mail, a bunch of things, right? So as a user, you come in. I just want to introduce, like, you tap on the finance app. It opens up. The first thing you see is, like, launch screen, right? You're engaging the user that, hey, something is going to come up which is going to interest you or what you're looking for. And then a famous thing starts, which is spinning and spinning, which my daughter says, right? Circling things. And then some of the components, while they're fetching data off the network, maybe it's not pre-fetched or something earlier, and it starts, like, spinning somewhere else. That, like, you'll see, like, based upon time, day, and probably weather, you will see different spinners somewhere on your screen. And then at the end, you have a fully usable experience, right? Which is your portfolio is there. You can see, like, what the indexes are doing on that day. You will see some of the videos, news, and bunch of things, right? So why is it taking so long to get the content, right? If you actually look at the app layers from a different perspective, when you're 20 years of history, just like we have in Yahoo apps, right? You start developing one app and then you decide that, hey, there will be some shared services like identity and push and payments and bunch of other things, right? And then you say, hey, you know what? I want to equip my finance app, my mail app, and my homepage app all with the news, and then you will make a shared component out of it, right? And then I showed here only 4 components, but it will just keep, like, creating those shared libraries or SDKs they call in mobile platforms, right? And then whole org is created called mobile platforms, and they will do all the shared services for you. Internally, app makes their own business decision that they call their own backend. All the services call their own backends as well, right? And they have their own cloud. And today, when we are, like, have a global concept, right? When you want to touch each and every user out in the world, a lot of these data centers are based off, like, in different locations, and all these services may not have presence in all the geographical regions, right? Some of them are on AWS for sure, but then if you're not using this approach and if you have on-premise, it's hard to afford to have, like, these data centers in every single region. So some of these services, like for us, identities and like US, and probably like we want to put some of the components in AWS, but then there is Europe, and then there is an India or APAC. But at the end, like do you know whether ads has the same data centers? Probably not, right? And all these calls, when you start your app, fires off and they go to different data centers, and then they like do their own things, come back and try to create this one launch screen or home screen experience for you, right? And I think that's the reason why like we learned out of our experiences, and actually Verizon or Yahoo, AOL, Tumblr, TechCrunch, all these subsidiary that created one group called Verizon Media has about 110 apps. And yes, you heard the number right. We have 110 applications in iOS and Android. When you look at like that kind of a scale, the things are important is to standardize some of the processes. And the way you do it is like hey, if you are launching your app and make it usable within 1.5 seconds, users will love it. We're gonna come back, right? But if you go in the territory of 1.5 to 5 seconds, and they're like, probably it's gonna come up. Let me give it some more time, and then at some point, like if it probably someone didn't like my talk, but or they didn't agree with me, but or some app, and then if you go to like 5 seconds plus, it's like okay, you know what, leave it. I'm gonna come back, and then as I said, my daily habits, I'll close my app and I'll just go to my next app that my daily routine is, right? Whatever the next set of things that I want to do. And while doing all this, one lesson that I learned, and I put it like very explicit ways, they're not gonna like show their negative experience, or they're gonna not show like dissent or something. They're just gonna walk away. They're not gonna go to feedback like our App Store or Google Play Store and submit their feedback. They're gonna not reach out to you, but it's like what, let's just leave it right here, right? So you may or may not get any feedback from the user, and that's why it's like very important for you to actually get things right, especially on your launch. Right. So now it's a nice segue to turn into measuring the app performance and why is it so hard and how do we do it. So well, it's not easy, right? I mean, especially when you are doing at the scale, it's not definitely that easy. And one of the things is, remember, like connecting back to our first slide, that when you come and say, hey, my app is working spotless, yes, but it's running the tests on the very controlled environment. All your hardware are plugged in, or your devices are plugged in. It has nice, like really like fiber optics level of Wi-Fi in your company, and you are not testing the real user scenario, right? And Bay Area so advanced, we have like 5G coming up, edge computing coming up, which like a lot of people are actually pioneering at, including Verizon. Well, at the end, looking at like APAC and other regions, for example, we're still living on 3G and 4G networks in a lot of areas, right? So when you are talking about globalization, like one of the things very important is look at like what kind of network bandwidth layers you have, and kind of slice and dice data. You really want to go to a level where you want to make sure you're not creating bias because of the high-end devices or better networks while you are looking at data, right? So basically, what you can do is you can go through the regions or geolocations, or you can do slice and dice data by devices. Like for example, Pixel has definitely better performance. Some of the low-end motorizer or LG devices on Android, right? Because of their capabilities. So you can do all these things. While one of the things that we learned is, as you said, standardization of processes is important. It needs continuous auditing, right? You need to continually look at what are the parameters changing. The world is changing so fast. The network capabilities, device capabilities, the regions, like availability of different kind of networking is really, really, really improving these days. And while everything is changing so fast, one of the very important thing is you continually look at and as I say, like slice and dice data based upon your parameters that you're looking at. Some of them, as I already talked, like we looked at different device capabilities, hardware, network latencies or network levels, those kind of things. Right? So I'm just gonna skim through some of the slides. Please do a quick time check and let me know if you're cool. All right, so we are right on time. So on iOS side, one of the things like that a lot of people kind of measures data differently is, if you see like here Hopefully it's readable. Um, the one thing you want to see is like, how fast you can go to the user, but then there are a lot of like, uh, I would say like, chunks that you want to measure. The first thing is like, OS launch time. Unfortunately, you cannot control that, right? When you start your app and until it goes to like, the uh, app launch finish with loading, which is kind of callback that you get, until that time, probably you cannot do anything, right? So speeding that up or measuring the data is not going to help you. The next thing is, while you launch the app, as you said, like, you are initializing a lot of services, initializing a lot of shared components, making a lot of backend calls, your remote config, you are trying to get some values out of network, a lot of things that you are doing. And plus you have cache, so you are trying to load all these things that matters, because now you really need to get into a level where you can identify like, hey, this component is actually causing the performance or cold start time increased on my app, because they are making like, making calls on the main thread, or they're doing something that they should not be doing, like, or while getting the user, they can always like, use the cache, right? And then they give a user feedback saying, hey, the user is logged out or something, right? So a lot of things you can do, and then from that point you want to put your home screen on and you want to start measuring that how much time it's taking creating their own UI components, the animations and whatnot, right? So we are slicing and dicing each and every single point of this data, and the way we did it is we actually crowdsource everything. So what we learned out of all our, I would say like, lessons or mistakes, that controlled environments are not a good measure of measuring your app performance or cold start. And the only way to do it is you put it out there, not only our beta users but all the users, and be really mindful of sampling those data, right? You have hopefully user consent and all the privacy is taken care of, but after that, whatever the data you get, be mindful about when you can send. You can queue it up on the app until you have a good Wi-Fi connection or something, but when you send it, use that data for cold start, battery, and your app performance measures, right? And then similar thing for Android. I'm just gonna skim through this slide, but again, it's the same concept. You basically don't want to just look at activity on create and on resume, but you wanna get like, each and every single piece of data from where OS starts or app launches to your shared services to your actual view to your animations, and then when the app becomes usable. All right. So going back to my cartoons. What is that one single thing that I learned out of 6 years working on so many apps and going through war rooms and got like late night calls from my executives, right? The one thing that I learned, and I wish I will knew before, is fetch all the content you have in the user viewpoint. And when I say viewpoint, it's your 5 by 5, 10 by 10. If you are on the iPad, it's like, n by n. And if you're on TV, 75 by 75. If you are 75-inch TV, for example, or 50, prepare something that user can go to that viewpoint as fast as possible, right? So just to give you a couple of examples, you might have like, very simple content oriented app where you, here I'm just presenting like, Yahoo Mail app. It has only mail content, right? And probably a single endpoint which gets you all the content. On the other side, you have like, we have taken an example of finance, and finance is doing a lot of things. If you see, this is completely different view than my portfolios because with very user driven view, and then we have some of the videos and we have some of the ads in between, and then if you go took a look at bottom, it has news and bunch of other things, right? What's important is what's in your viewpoint, and you want to prepare that fast. And the way we did it, and I think that it's not a magic, right? I mean, you can do everything that uh, the people do, like, use tools and look at app performance and everything, but the one thing that saved us a lot of time is reduce the network a number of network calls that you need to make. The reason, it's very simple, right? If you have one network call going to a data center, and it's actually forking like, few more calls to get all these ads and identity and video and news and everything, right? Those calls are inter data center calls. Even if they are inter data center or intra data center, they're going to be faster than the user can experience those calls on 3G or 4G network, right? So the first thing first is like, make one call that actually gives you, it can spawn to multiple microservices and whatnot. But at the end, it should collect all the data and give it to you so that you can do a lot of things in a one call. So that user can have perceived latency measures, like pretty much summed up to just one network call, right? And then I have some nice to haves, like you can use app cache, you can have background fetch that you have like periodic background fetch on iOS or something. You can use silent notifications. On Android, everything is silent, so you can use that to prepare your data even before the user launches the app, right? The network layer optimization that Subodh is going to go through like in more details, and what Codever does as well. And then user feedback for making sure like that user is not just hung on something. They have some feedback, spinners, dots, whatever the way you want to present it. But at the end, what matters is fetching content that fits in your viewpoint in your home screen, right? Cool. So I think that's all I have to present. We'll have the slides shared, right? I mean, I'm just making it curated through the company. Once it's available, I can put it on Slideshare and give it to you. And feel free to reach out to me for any questions.
So I do relate to the children experience. I believe that children are like the most honest users. Like I still remember my 9-month-old still not walking, climbing to the TV and sliding, and she was very very upset of the fact that the TV did not slide. So I do have one question for you. So don't run away. I was curious about. So you collect a lot of data from in the field, so from real users. Do you use that data in any way so that you can mimic user conditions before launching? And if you do you use that in, for example, developing processes like integration testing?
Yeah, it's a good question. So basically, we do that, right? So we call it sampling data. We sample some of these things, and we can actually like create a real mix that kind of works well with our audience. And basically, we look at like high and low end and like mid range, both network as well as like the devices, and we run on them like on a basis. So as I said, like the median is not a good way because it creates a bias for you, right? Because if 70% of people on the planet has already high end devices, then you're gonna ignore those results from the 30% of the users, right? So what we do is we sample data, we actually create a feedback loop which actually mimic those same experiments. We do have in-house device lab, something we call, which has a different variety of devices, actual devices, and we simulate some of the network conditions based upon what iOS and Android gives you, and some of them like are actually putting the test hooks within the code, right? Only compile it out with the macro or something, but actually put that code in, so that what it does is like it tries to mimic some of the network conditions. So even if the response is faster, we try to make sure like that we don't give it to the UI or something and make sure it's not crashing, right? So yes, and it's all part of the CI/CD pipeline. So we don't like differentiate between desktop and mobile as like two different entities. All our mobile drops, including all the library drops, also should be high quality. And so it runs first like all the function integration, and then it runs through the cold start time, and cold start measures are good, then it will go through actual real world conditions and simulate each and every of them, right? All these things run in parallel on different devices, and at the end, if the pipeline is blue, that means everything is good. If it's not blue, that just means that you broke something. And before anyone else identifies that, you should be like fixing that. So yes, we do it. We do use them. We do collect them. We do make sure that the PII is gone from this if we are sampling based upon user or something, or the geolocations, and we just use them after removing the PII.
So I'm not sure if anyone else has another question.
Normally, we can relate this.
Yeah, sorry guys. Normally, when I believe we can relate to this, is that every time you want to develop a feature, you have like this triangle of responsibility, right? We have the guy responsible for the product that defines the feature. You have the engineer that actually implements the feature, and then of course you have the designer that designs the experience of the feature itself. And at least as being as an engineer, our point of view normally is trying to do the feature as best as possible, as fast as possible. But normally the design guy doesn't like this approach. He likes something more beautiful. He wants an animation. He wants that splash screen to last for exactly 2 seconds because it's cool. It showcases our brand, his logo. is background movement, is flow of wind or anything. So, in your opinion, how can we manage these desires of slowdowns, purposefully uh, slowdowns with purpose, like from the designer guys, with the need for speed that engineers normally have?
So I think it's a tough question to answer. This reason is the reason why you are animating is because you want to slow down the user. Really, right? I mean, animation does nothing but it gives you or buys you more time as an engineer to do something before, like, it completes and you have, like, kind of data available. Well, I think that there's always healthy debates, right? I'm not denying the fact that there is, like, designers have their own world of our, like, view of the world, and then engineers have their own view of the world, right? And the way I think that we fine tune it is that there are two things, like, is one of the thing is like, hey, whether it actually adds up to the user value and user feedback. So first thing we look at from that perspective. The second thing is definitely, like, if we learn from the experiences, we use that. The third thing is we try it out with user studies. So we do a lot of user studies, and we actually nullify some of the components which actually doesn't need. So yes, I mean, fine, on one fine day, my designer says, "Hey, I want to animate this thing, or I want to, like, put this jazz influence logo. Let's find out a strategy that if we can cache it, like, it shouldn't be moved." One of the biggest problem with the client world is you cannot force users. It's not your server typical day-to-day work, right? And then when, especially when designers work in between or shared in between browser and native experiences, and they were like, oh, you know what, tomorrow we'll change it. Guess what? Be my guest, but we cannot do it, right? Even when you have auto downloading applications and things turned on, people may not like update their like, applications at all, right? So one of the things that we actually do is the user studies and a lot of focus on the users. The second thing is we time bound a lot of things, right? So as a part of, like, sprint planning, we make sure that they understand, or it's our job to make them understand why some of the things or some out of this world ideas are not possible, but, like, we can ship it as a next layer or something. And then one of the things I wish that I think some of you guys also would agree to me is in some of the next versions they actually provide dynamically loading the assets, right? Some of the launch screens and whatnot. I have been requesting it like every single year in WWDC, but I didn't see that. But if there is something like that happens, then it's going to make this debate very easier. But to sum up, user studies, uh, like, whatever the performance is and why we are doing it is really important. Third thing, we can test it out. So we put it out in actually alpha and beta users. And before that, even dog food within the company has 10,000 people, should have really good feedback. We do some of the cafe studies as well. And after that, if we agree, then we go for it, like, and then we time bound the approach as well. And if we go out, then we start measuring whether it actually increasing engagement, and that data helps you kind of, like, push back next time when someone comes with you with their own like, view of the world, saying, hey, this is what is important, but hey, you know what, we should the exact same feature in payments and it didn't, like, drive any user engagement, then why we want to do it, like, for identity or for push or whatever other services or app that we are looking for. Does it answer your question?
Now, Subab to tell us all about how networking protocols affect mobile app performance, or is challenges around it. I guess you're all set.
It's been a while since I used Windows. I think that means full screen.
Control L or something like that, or F.
Sorry. Oh, wow. Pro, strong heart. Hey guys, my name is Subodh Iyengar. I lead the transport security teams and the transport engineering teams at Facebook. And so over the last 7 years, I've been at Facebook for about 6.5 years. In the last 7 years, we've been working on speeding up mobile networking in general, and our mobile apps and our load balancers for both browsers and as well as our mobile networks. So I'm going to share some of the lessons we've learned throughout the years, and hopefully by the end of the talk, you take away that Even though you don't own the kernel on the mobile apps, you can do a lot of stuff to speed up mobile networking performance, and it does matter. Oh, yeah, that's the next button. Nope. How do we go next? Oh, excellent. Thanks. So, quick overview of the talk. I'll talk about some of the bottlenecks that we found in our experience in mobile networks. I'll give you an overview of Facebook's load balancing infrastructure, and so that it helps you understand the rest of the stuff. And I'll touch on some of the interesting things we've done in networking performance, covering the new protocols that are coming out and what we've done to deploy those protocols. And so the whole talk can fit in like, I can keep talking for like 4 hours or something, but I'm going to try and fit it into like 20 minutes. I'm very verbose, yes, especially after a glass of beer, yeah. So you try and fit it in within 20 minutes and try to talk about it. So generally, like all mobile bottlenecks, all generally not specific to mobile networks, bottlenecks can fit into two categories. You have like your bottleneck by throughput, your bottleneck by latency, and there's errors as well, somewhere sitting in like kind of the devil in the details. But really, like throughput keeps increasing year over year. You get your $50 plan from Comcast, Verizon, even though the spinny dialog shows up, it buys you 10 gigs a second. Next year, it'll buy you 100 gigs. Who knows, based on a privacy policy plan. But the real devil in the details is the latency. So latency is limited by this pesky thing called physics. Damn you, physics, laws of physics. Whichever kind of physical model you subscribe to. So really the thing that bounds you in the latency is like how long does a request take since I made it to getting the response back. And that's really limited by this thing called round trip time. So if I am closer to the user, my round trip time is less and the latency is lower. If I'm farther away from the user, the latency is higher. So obviously this kind of like is intuitive notion that if I send my packets and I get my responses back, it takes me a round trip time. But actually it influences a whole lot more in latency as well, not just how long you take to get packets to get back. For example, before you can send your request, you have to set up a connection. And the connection setup takes more time if your round trip time is higher. You might lose packets. You're in a wireless network, you lose packets randomly, or lose packets due to congestion. Recovering from the packet loss is also proportional to your round trip time as well. So you have to get feedback from the peer to tell you whether or not if they've received the packet or not, and then you can retransmit that packet. Related to this problem is another problem you might have heard of called head-of-line blocking. So if you lose a packet, and even though if the peer has received all the other packets, they can't read all the other data out until they receive that one packet which is blocking them. So head-of-line blocking also takes a lot of time. And errors, dealing with errors, like Swapnil covered it pretty well. Like you have to kind of deal with errors to show users a good message. You have to retry things and get things like so that you actually get the response back to the user and show the screen to the user at a particular point in time. So this stuff can take a lot of time to talk about, and there's a lot more. I'm just going to focus on this one particular aspect of networking performance, which is connection setup. A lot of people have talked about app startup time, and connection setup is like perfect to talk about now, and like the concept of networking performance, what influences app startup time. So before I get into connection setup time, I want to give you an overview of the Facebook load balancing infrastructure. It's like a 100-foot level overview, but generally we control all the aspects of load balancing, all the software that runs in every single part of this ecosystem. So we have these machines that run in locations which are closer to the users. They're called edge pops. And so they run a load balancer called Proxygen. So Proxygen is actually an open source library. It's a toolkit to build HTTP clients and servers, very high performing HTTP clients and servers. We built a rev proxy out of it, a reverse proxy out of it. So when we're sitting very close to the users and users send us requests, we terminate those requests. We terminate not only the TCP connection, we terminate the TLS connection and also the quick connections as well. I'll talk more about that in the end of my presentation. And then once we terminate them, we decide where this request goes to in our backend infrastructure. For example, if the user's data is in like Oregon, we'll decide we're going to send the data to Oregon. And this is done over something called our backbone network. And so backbone network also uses HTTP2 or HTTP3, and it goes to our origin load balancers, which stay in our data centers. And that gets forwarded to HHVM or the cache service or whatever service is there. In this case, let's say you're downloading your cat photo feed, and so this will go to your HHVM service, and then like HHVM, which is a PHP runtime, decides what photos to render to you and what data to render to you. So meanwhile, there's also the mobile app, which is making these requests to our load balancers as well. So we actually control the networking stack, which is running on the mobile side as well. Unlike browsers, in the mobile apps, you control your own networking stack. So many people might use a default NSURL session. Many people might use Android OKHTTP or something of the sort. We actually built our own mobile cross-platform networking stack. It's based on C++. So it compiles and actually runs on both Android, iOS, as well as our Edge load balancers as well. So it's actually the same code that runs on both client and server, and also on Origin as well. So it runs on all the sides of things. So and then we are able to, because we have the C++ library, we're able to plug in our other open source libraries. So for example, Fizz is our TLS 1.3 implementation, which I'll talk about at the end of the presentation, and Move Fast is our quick implementation. So we're able to do this, plug these in, and kind of experiment end to end with new protocols and new things to speed up networking. So what the edge load balancers end up doing is like it helps us defy this law of physics, which is that you need to get closer to the users. So we get as close as the users as possible. So, but what happens, even though we're close to the users, what happens during connection setup? So you guys have definitely probably heard of this before, like either in your textbooks or something, or in a pesky interview question somewhere. So I'm not going to spend too much time on this. But when you, for example, have to talk to example.com before you send a request to example.com for cat photos or something, you have to get a DNS. You have to know what IP address to contact example.com. So you do a DNS query. So that's one round trip for the DNS query. After that, you have to send the TCP packet to set up the connection. So you send the TCP SYN packet to that IP address. And the server responds back with something called SYNAC, which tells, I got your SYN, here's my SYN as well. You do something around it. So now already 2 round trips have passed. You've not done anything yet. You've not actually sent the cat photo request yet. The 3rd round trip, hopefully you're using HTTPS, everyone, and you have a secure connection. So the 3rd round trip, you end up sending the client hello, which is the initial packet, which is the TLS exchange. So you send the client hello, and along with the piggyback the ACK for the TCP request, and then the server sends you back the server hello, which is the response. So you've not sent any app data yet either. 3 round trips have passed, not sending any app data, which is not great for app startup time. And now finally, you're able to send app data and piggybacking along with something called the client finished. We don't have to know about the details of the TLS handshake here, but the client finished is something which tells you that I'm done with the TLS handshake, and so you send app data along with it. So it took 3 round trips, for instance, to establish the connection. So 3 round trips, not so bad. Networks are getting really fast. You're really close to users, right? Like, what could the big deal be? So we measured, for instance, what the connection setup time is inside the network. So this, for instance, is just the TLS connection setup time. This is measured from Android apps on mobile networks. They run on Wi-Fi and mobile, just overall. So, for example, a 75th percentile you can see at all over the world is about 200 milliseconds. So it's pretty bad, for instance, if you're trying to get, like Swapnil was mentioning, you're trying to get within 1,500 milliseconds or something like that. Yeah, so this includes all retransmissions of, and multiply this by 3 because you're doing 3 round trips. You can cache DNS and stuff like that. So maybe 2, it's fine. And in India, it's worse. And in 2G networks, it's even worse. So clearly, connection setup time is a problem. So we cannot go around setting up connections for every single request that we make. So we have to do something about that to alleviate the cost of connection setup. So clearly, the biggest lever in your hand is to reuse the connection. So once you have a connection established, just keep reusing that again and again. Now, usually what you see is the app request patterns is that requests show up in like bursts. You start up the app, like everybody wants to make a request right now and then. You scroll through your feed or whatever app, everybody wants to make a request at that particular point in time. But how many of you use HTTP 1.1 or are aware that you're using HTTP 1.1 at the moment? No one? Raise your hands. No one wants to admit it. Yeah, so HTTP 1.1 has this pesky requirement. The semantics of the protocol don't allow you to send multiple requests down the connection at one point in time. So you actually have to send, so let's say you have request 1 and 2 that show up at the same point, and you have a connection alive for both request 1 and 2. You have to send request 1, wait for the response for request 1, and you read out the body and the headers and everything completely, and then you can finally send request 2. So that's really shitty. You waited for 2 round trips, or actually even more than that. For example, the request might need to go to a backend, and like, so that's even more round trips that way. So what you'll end up doing is you'll open up a new connection and send request to. So you end up connection reuse doesn't really happen in this case. So the first thing we did was really like, we were like, this is several years ago, but we used HTTP2. So we're using Speedy before that, which is a precursor to HTTP2. But what HTTP2 allows you to do is that you can actually multiplex several requests on one connection at one point in time. So you establish a connection. So if requests 1 and 2 show up at the same time, you can actually send the requests at the same time to the server. And the server can respond to those requests in any order that it wants. It can send bodies interleaved with each other, and you can still handle it. So basically what you end up getting is that you end up with one connection, and you can reuse the connection like any number of times you want. There are some caveats to that. So we also did some various other tricks with the connection pooling. We do pre-connects. We do something called late socket binding with the connections as well. We do several other advanced session manager tricks. And so as a result of all of that, we got pretty good connection reuse. So that means like for all the requests that we see, our connection reuse is about 86%, and that really depends on your request patterns, but this is request patterns of the Facebook Android app. And what we see, though, is that in India and in 2G networks, though, the request connection reuse rate is much lower. So there's several reasons for this. For instance, like if you have a flaky network, what ends up happening, your network will start dropping packets, TCP will close the connection, your NATs will rebind yourself. So you have like very large NATs in 2G networks and in emerging market economies. So what will end up happening is that HTTP connections have a lot of idle periods of time. So you'll send a burst request, you go idle, you send a burst of requests again. And within that idle period, your NAT could have like dropped the connection. So ends up happening is like you get TCP reset when you try to send a request. So you will reuse the connection less. So the next step, logical step in this process is, okay, so we got this much of connection reuse. We spent a bunch of time. We spent several years actually like improving connection reuse like to this level. And so the next process is basically we need to be able to speed up connection setup time. So how do we speed up connection setup time so that it takes not 3 round trips? So let's cut out the DNS round trip because we can cache stuff. Let's say 2 round trips now. How do we speed it up from two round trips to 1 round trip? So what we did was we actually deployed TLS 1.3 in our application. So TLS 1.3, if people are not aware, is the next generation of TLS. So TLS 1.2 was the previous version of TLS. That was standardized about 10 years ago. So that's how long we're talking about. So not only is TLS 1.3 more secure than TLS 1.2, like a lot of mistakes were done in the security design of TLS 1.2. We really didn't know much about cryptography and protocols like 10 years ago. Honestly, like I've been through this process. It's like, yeah, exactly. So what ends up happening is TLS 1.3 is like, let's redesign it from scratch. And it sounds like it's TLS 1.2, but it's actually like a completely different protocol. One of the more compelling use cases for performance of TLS 1.3 is something called zero round trip time data, zero round trip data, or something that's called early data in the handshake. So we actually participated in the standardization process, and we contributed a bunch of stuff to the standard. And we implemented our own implementation of TLS, which is called Fizz, and so our team worked on that. And we actually now have the largest deployment of zero RTT and TLS 1.3 on the internet. So more than 50% of our traffic to Facebook from our applications, as well as Chrome, as well as Firefox, as well as other browsers, actually use TLS 1.3. So it's real, it's deployed, people should use it if you're not using it already. So how does early data really work? So like I showed previously, to contrast the TLS 1.2 and TLS 1.3 handshakes, TLS 1.2 is on your left, TLS 1.3 is on your right. So you can see how it required 2 round trips before you could send app data after the connection was established. But in TLS 1.3, what you can do is just after you get the SYNAC from the server, you can start sending zero round trip application data immediately to the server. So you're kind of like, think about this as like you're piggybacking data on the handshake. So while the handshake is going on, I'm going to send some data along. And the way you do this is that you remember some keys from the previous connection, and then you use those keys to drive a special secret, which you can encrypt the application data with. And after you get the handshake from the server side, you derive the 1RTT keys, which are more secure. I'll tell you why in a bit. And then you can send the 1RTT data after that. Great. So the problem with 0RTT data, there's a subtle thing with 0RTT data, though. It doesn't come for free. There are various security implications of 0RTT data. You should not use 0RTT data just for all of your data you send on the app. For example, let's say that you're sending a request for buying phones, like buy a phone from something. So the problem with 0RTT data is that the server has not had a chance to mix in its secret into the client's key that it's using. So what an attacker can do is take that data that you send, the 0RTT data, and repeat it ad infinitum to multiple servers and cause the transaction to happen multiple times. So you could buy like 10 phones, 20 phones, whatever. So the thing is that you should only use 0RTT data for data that is idempotent or replay safe, or things that already have replay safety semantics built into it. So if it happens multiple times, it doesn't actually affect the security of your application. So we have various protections in place at Facebook to prevent 0RTT data from being, not only do we have replay cache, we have like timeouts for how long the 0RTT data is valid, and multiple layers of protection to prevent this kind of attack on Facebook Infra. 5 minutes, okay. Whoa, it's tight, okay. So as expected, like you'll see the 0RTT data actually kind of reduce the connection setup costs like by 40% and a P75, so that's really great. And overall, it also reduced it by, overall of all requests, it reduced it down to 2%. So why do we care about this, like if it's only reducing it by 2%? Because the very key interactions of the application, like we're starting off the app and stuff like that, do depend, are very influenced by connection setup time. So we want to improve them at 40%, and we did improve cold start time as a result of this. Great. So now that we hit the limits of what we can do with TLS and TCP, we're looking at the next generation of what we can do with for improving network performance. So Quick is a new transport protocol that's actually being standardized by the IETF, and we're actively involved in the process, Facebook and our team. And so this is so Google had the original version of the protocol, but the IETF is developing a completely different version of the protocol based on the same semantics, but it actually is way different. So IETF Quick and Google Quick are completely different entities. So if you think about it, like what does Quick do? So if it's a classic OSI layering model is like you have this application, you have HTTP2 on top of it, you have TLS on top of it, and TCP on top of it. But the problem is that this separation between the layers creates some performance characteristics like, oh, it takes one round trip to set up TLS, and it takes another round trip to set up TCP. So the reverse order. What if you could munge all of those things into one and piggyback all of those connection setups at one time? So that's what Quick does. So we're interested in Quick because not only does it provide, so we could have built something custom, but standards are great. We have to actually interrupt with Chrome, Firefox, all the other browsers. But we also want to make it such that we have an extensible platform on which we can develop custom protocols and custom things to make our app faster. So one of the things, I'm going to talk about one of the things that makes Quick like really compelling to us, just in the theme of connection setup. So I'm going to skip this. So it's Quick, okay, I'll probably explain this, yeah. So the Quick's fundamental abstraction is in multiple streams of bytes. So instead of having, so you can think of this in HTTP2, but if the transport understood HTTP2. So multiple streams of data are sending data at once, and you can read them out of order between each other. So even if you lose, for example, data from stream 0, you can actually still read out stream 4 and stream 8, data from stream. So this alleviates the problem we classically known as head-of-line blocking, that is like multiple streams of data interfering with each other with one connection. So also like things that you can do with this is that if you cancel a stream, you actually not only cancel the data, but you actually cancel all the retransmissions of the data of the stream as well. So it ends up being like, it's like HTTP2 on steroids. You can think of it that way. So how does 0RTT work in Quick, and why is it faster than TLS 1.3 0RTT? So one of the things you can do with Quick is because all these layers are munched together, you can piggyback the TLS handshake that's happening along with the connection setup of the transport as well. So when the transport is setting up a connection, instead of sending a SYN or SYNAC, it just sends a client hello directly to the server and says, here's my client hello. And also in a separate packet, it could send all the data that it wants to send in 0RTT as well at the same time. So it actually sends all of them at once. And then when the server receives this data, it's able to respond directly with the 1RTT data, which is the response data for your server, for your client's requests. So what ends up happening, and then the client then continues to use 1RTT keys. So what ends up happening is that now your connection setup is 0. You could send data, you have a socket, you can send data directly. If a quick socket, you can send data directly to the quick socket. You don't need to wait for the server to say hello to be able to send data. So that's really fast. So we've actually not only been interested in this protocol, we've also been deploying this protocol over the last year. So we've run some tests with API-style requests so far on their smaller requests and responses, and we have some very encouraging data around them. So not only this is this experiment is basically Quick versus Quick 1RTT versus TLS 130 RTT. So this is not even exploiting the 0RTT capabilities of Quick at all. So what we find is that the latency of P99, for instance, is reduced by 23% when using Quick. So what we think is that it's the major win of Quick is coming from the loss recovery of mechanisms of Quick. That is, Quick is able to recover much faster from loss because it has much richer ACKs, application level ACKs, and it has transport level ACKs, sorry, and it is able to retransmit a little bit more aggressively and honor application deadlines better than TCP was. TCP is generally very conservative of retransmitting the data and actually like recover from application loss. Great, so we have a lot of future work to do. We're exploring things, we're using Quick as a platform. So we're actually exploring things, ideas around Quick, like how to do things like partial reliability for things like video. So video decoders can do things with even partial data. So how does the transport get out of the way of video decoder? So it's like, let it do its thing. It can deal with recovery, loss recovery, and error correction. There's a lot more work to do in loss recovery. We've only scratched the surface. We have actually seen a lot of cases in production. I have some backup slides to go over how, if you're interested in how we debug Quick. But there's a lot of inefficiencies in the current loss recovery mechanisms that we would love to address. And we also want to deploy the latest versions of Quick as well. So why should you care, like generally, about networking? Your data that you send gets sent in packets finally, and those packets are sent over a network, which can lose packets, and it has physical limitations around the data. So you should ration about that when you're sending large payloads. You should reason about it will take longer to get there because it will take multiple round trips of data to get in. So you should ask if you're using a CDN vendor or like a library that you're using. You should ask them for like, when can I get TLS 1.3? When can I get Quick? When can I speed up my connections faster? How can I reuse connections more effectively? Like put in logging for seeing how much connection, what kind of reuse you're getting for connections. And there's a bunch of major infrastructure changes required for Quick. I haven't really touched on them at all. So it will take them time to get to those points. So ask them now so that eventually they will get there. And like a year from now, you'll get these features. It's great. So great. I don't know whether we have time for questions. I'm Subodh on Twitter if you want to follow. Yeah, that's great.
So I do have one question for you, but let's see if the audience has any questions for Subodh.
Just kidding. So what you were saying, like the G Quick, right? And I kind of read about it as well, and wanted to understand, like why there was a separate channel developing the similar standards, while I think they're kind of early adopters, if I understand correctly, right? So just like if you can give me like top one or top two differences why it has to be a separate effort and how it's gonna impact overall in performance. One is better performant than the other, or how it works.
It's a great question, Sohail. So Google originally developed Quick, the G Quick version, and then IETF, they brought it to the IETF to standardize the Quick. So it's actually like nice of them to do that. And so I think Google Quick only addresses, I think for a lot of reasons, Google Quick only addresses the requirements of Google. And so IETF Quick actually addresses a far wider set of requirements. Yeah, so it's more community driven. So one of the examples of this is something called the connection ID in Quick. So the connection ID is a persistent identifier of a connection across 5 tuples. So the problem with UDP versus TCP is that some helpful middle boxes inside of networks actually understand TCP. So what they do is if you're running a NAT, then you can see when the TCP connection starts, and you can see when the TCP connection ends. So you can actually keep your timeout. You can keep a very large timeout. So 15-minute timeout, for instance, for your TCP connection. However, for UDP, you don't know when the flow starts or ends. So what they do is they keep a very short timeout for connections. So what ends up happening is that their NAT rebinds quite a bit if you have a longer-lived connection. So you need something which identifies a connection beyond just your 5-tuple, which is for people, it's their source port, destination port, source address, destination address, and your protocol, which in this case is UDP. So the thing that's called the connection ID is sent with every packet in the quick payload in the connection. This helps servers identify it. So in gquick, for instance, there was only a notion of client choosing connection ID. That is only a client chooses the connection ID, and then the server just keeps using that connection ID all the time. So when they took this to IETF felt that there were a lot of DOS vectors with this, and it also limited the infrastructure that a lot of other people had. So we introduced this function called a server-chosen connection ID. So if a client comes to us and tells us, like, hey, by the way, this is our client-chosen connection ID, the server can say, no, use this connection ID for the rest of your connections. And so what you can do with that is actually, not only does this help you prevent against DOS attacks, it actually opens up a whole new range of features. So you can encode bits in the connection ID to help you with the routing of the packets inside your subsequent packets inside your infrastructure. It basically becomes your new IP address, kind of, if you think about it. And so it helps you like do a bunch more things. So that's just one example of the thing that's happened. So another thing is like it adds better security. For example, gquick had a different cryptographic protocol called Quick Crypto. That had some analysis, but had very little analysis. Actually, even when we were developing TLS 1.3 before that, we had a protocol called Zero Protocol. There's a blog post about it if somebody wants to take a look at it. But we found a bunch of vulnerabilities in Quick Crypto, and it had way looser security properties in TLS 1.3. So just the replacement of the security protocol itself makes the protocol way more secure and stable and way more private as well. So there's a bunch of changes there. It solves more problems than just Google's problems. Yeah, they are. They're working on this right now in building IETF Quick into Chrome, and hopefully in a few months it should be out there.
So one question for you. You mentioned the fact that obviously latency affects not only the connection establishment but also the packet loss recovery. And you mentioned that in Quick, IETF Quick, you are changing the way you handle that. So I'm a little bit curious, how do you become more aggressive, as you said, with respect to what TCP does?
Yeah. So obviously, so that means to give more context around, to give more flavor on that thing. The fundamental problem is you don't know when loss happens because you have to approximate. No Oracle tells you that the packet you sent was lost on the network. You have to approximate. You have to use heuristics to detect whether a packet is lost in the network. So usually the way that TCP does this is that it uses several heuristics, something called do-back threshold, a combination of retransmit timeout, for instance. So do-back threshold means if I get ACKs for packets, which are not the next expected packet that I was going to get an ACK for, I will kind of assume that, maybe my packet was lost, and I'll wait for a little bit of time. Or RTO, which is like the fallback mechanism of TCP, which is that if I don't get any ACKs at all, I'm just going to assume that something really, really bad happened, and I'm going to retransmit those packets. So Quick has several different functionalities of how it deals with loss. For example, it has in SAC, because in TCP SAC blocks, you can only fit maximum of 3 SAC blocks in a TCP option. So it's very small. So SAC blocks are ranges of ACKs. So if you're sending a large amount of data, you can only fit a very few small amount of data. Quick does not have that limitation. You can send like as many SAC blocks as you want, and so you can encode way more information in an ACK. So The next option is like the way that TCP deals with RTO is very different from the way that Quick deals with RTO. So for example, when you RTO, TCP immediately reduces the congestion window down to 2, the min CWIN, which is 2 at the moment. But Quick adopts a slightly different approach. Instead of like reducing the CWIN down to 2 immediately, it only does it like when it knows that the RTO actually was verified. So what TCP has to do is sometimes it happens, spurious retransmissions happen. And so because you too aggressively detected an RTO, like your timer was too low in an RTO, and then you finally get the ACK and you're like, oh my God, I screwed up. Hey, what happened? So what it does, it tries to undo itself, the CWIN. And so it's really inelegant algorithm, which has a lot of bugs and stuff. So Quick tries to like reverse that and say like, we're only going to reduce the CWIN when we know that the loss happened for real. We're just still going to limit you by CWIN, your current CWIN. If we assume that your CWIN was this much, that means we had somewhat assessed your CWIN was this much. We're going to allow you to send till this current CWIN, and then when we know that the RTO really happened, we're going to reduce. So these subtle things actually build up, like these small subtle things build up, and like actually, it is even though the fundamental algorithms are the same, that is like, oh, I do back-based recovery. The spirit of the algorithms are the same. The implementation of them is like very different from the original implementation. So it's like it acts different. You see it acting differently.
Thank you.
Yeah.
Thank you.
Yeah.
So very quickly before the beer, let me invite the speakers here so that we can. Yeah, very short. I guess we are all hungry and especially thirsty. So first of all, thank you for coming. Very powerful messages. I guess that we went through from monitoring to actually looking at the impact of how, in your case, you mentioned a very simple example of just bootstrapping an app. How does that impact user experience, and then how networking protocols affect that. So my question for you, all of you, from your different perspectives, is first, how is network calls affecting this? How relevant are network calls with respect to app performance from your different perspectives? And what do you believe are the next steps to optimize this from the both app development and as well as networking protocols?
So in our case, we actually do a lot of what he talked about collecting all of the initial app launch request into one endpoint. So there is exactly that endpoint, which does a simple app startup request that is a big blob that has everything the Uber Rider app needs to like sort of bootstrap itself. And of course, we do cache the previous session. But even though we cache the stuff, the latency is a big deal because, for example, if you are not on a trip before you like killed the app and then you're now on a trip, you get this very discordant experience where you start up and you're in this screen, and then finally that one thing, even though like we do the optimization of having a single endpoint, when it finally comes back, you get this weird thing where it suddenly realizes that you're actually on an Uber trip, and so then the map slides over and then the route lines show up and stuff. So you get this big jarring effect when that response comes in. So for us, like, even though we try our best to optimize that stuff, that key call is still a problematic thing for us. And so whatever, again, I sit next to the teams that work on the kind of stuff that Subodh talked about with trying to use different sort of network transports and stuff. That's still a big deal for us because I guess my point is that even with caching and stuff, just because the cache data can be so different than your current state for the app, especially for our app, because like you open the trip when you're at the beginning of the trip, and then you close the app, and then you open it halfway through. The state is so different that latency still matters, because then you get this weird flash, and then suddenly it realizes, oh no, you're not there anymore. You're almost at your destination. So it still matters to us, and whatever we can do to speed that up is a big deal for our app.
I was just thinking what I can add more because my whole talk is based upon the network, right? So it's very important, like, as I said, if you want to create that customer love and brand loyalty, but at the same time, one of the things that we really learned is while everything is important, the security is also important, right? SSL pinning and bunch of things, TLS improvements. Though it takes more time for encryption and decryption, it's very important. Uh, but beyond that, I think that I like the other ideas like zero RTT and TLS 1.3. I think we are also adopting as company as fast as we can. We just recently moved to a 10-year-old thing, TLS 1.2, and we made sure and I think a lot of things is driven by like I should give a little bit of credit to Apple as well. So they shut down TLS 1.1 completely. So you as a server or as a backend services, you don't have that option anymore. But just want to say one thing, yes, network latency is very important, security is important, but at the same time, usability is important. That's the reason why network is very important, right? And don't forget about your 3G and 4G users, because as Subodh said, and I experienced myself as well, being native Indian, and I often visit there. They're still living in a case where 3G and 4G is like a luxury, right? It's something you usually work towards. 2G is most prominent thing in those countries. So don't forget about those 20% users, because when you're talking about millions, 20% account for a lot more than what you think.
Yeah. I mean, the whole talk was on networking, but yeah. Yeah, I think it's kind of hard to tell generally. Like, what, for example, if someone replaces a blue button with a red button or something like that, like that's going to completely change user behavior. And in the networking space, what we're doing is we're making incremental progress to basically make the app experience or a little bit faster than it was before. It's not going to fundamentally change things, but I think, for example, from the networking side, what can fundamentally change the products that we build is things like VoIP calls and stuff like that, right? Like, though, if there's no network feature that allows you to get very, very low round trip times and very, very low real time latency, you can't build a VoIP product. It's like not possible. People will not even use it. If you're building it over TCP, nobody's going to use your product. And so, like, the networking really, really matters there. I think, for instance, for the just normal HTTP, like video on demand downloads, think about like what the deadline characteristics of your payloads are. So, for example, if I want it right now, you might adopt a different approach than if I want it later. From a caching perspective, I think some people talked about caching as well. I think Swapnil talked about caching and talked about caching. So sometimes actually, like, there's very specific things in the mobile platforms themselves, which are very surprising. For instance, Firefox and Facebook have done various experiments to say that actually, if you try to read from disk, if you're trying to read from flash, it's actually you're probably better to just go and fetch it from the network and back, because your flash is so slow that it's not even going to give you back the result. So things like where you're on the mobile network, you might as well, your network is actually pretty fast. And if you can make your network connection and requests very fast, you can do innovative things where you can race your request with a cache miss. And so you'll probably find that you'll win, the network will win most of the time as well. So I think those are the interesting next avenues in network. What are the things that what are the new products that more modern networking can enable, which are not possible now? Yeah, so all is pretty broad there. So, for example, I think that fundamental design decisions are made inside of protocols which obviate their use in certain situations. For instance, if I'm using Quick right now, I'm not going to use it in data centers like in very high QPS services, which really care about CPU at the moment. I'm going to wait till, for instance, they implement some sort of NIC offload and then maybe use it. Or maybe it's not really that, like, if I'm inside like a some microsecond network, I actually don't really care about network at all. So it really depends on what you mean by all. But inside the internet, I think that there will be certain solutions developed in the future. Like, hopefully it'll be like a knob you can twist, right? It'll be like, I want better latency and I want better responsiveness, and then you will twist that knob, and suddenly you get a new protocol will pop out of it.